Dear students, today we are going to see YBus, that is bus admittance matrix. In the previous classes, we have seen regarding incidence matrix, primitive matrix, many things. So today we are going to see what is bus admittance matrix. For your syllabus, we are going to see two different types of YBus formulation. One is YBus using inspection method. Another one is YBus using singular transformation. First, we are going to see how to build a YBus using inspection method. Very easier method, and by seeing the network directly, we can write the bus admittance matrix, which is much more required in solving the many problems like load flow or its solutions using Gauss-Seidel method and Newton-Raphson method. Many things we require this YBus. So let us see how to go with the inspection method. See this figure perfectly, where we are having three nodes that we have shown with the circled one, 1, 2, 3, and there are 6 admittance are connected, and the one bus is taken as reference bus, that is what the bus 0th one. So what where the all y1, y4, y2, i2 and i1 are connected, the bottom one we can consider it as a reference bus. So how to go with this YBus using inspection method? See, let us apply KCL at the different nodes. So usually in our inspection method, we will leave the reference node. Directly we will get the YBus. Means our YBus is a matrix of size node cross node, means node into node. How many number of nodes are there, that many numbers of rows, that many number of columns will be there, and these nodes are nothing but the nodes excluding reference node. So by seeing this figure here, total 4 nodes including reference node, but the size of the admittance matrix is 3 cross 3 because one is reference node. Fine, let us apply the KCL at the node 1. You can see here entering current is I1 and 3 admittance are connected, Y1, Y3 and Y6. Before that we will consider that at node 1 voltage is V1, at node 2 voltage is V2, and at node 3 voltage is V3. If you are going with the same data, see at node 1 we can write it as current I1, where I have shown you I1 is equal to what? Y1 V1, that is admittance of the element where it is connected from ground to first node into V1 at the node V1, and Y3 is the element which is connected between node 1 and 3. So the voltage difference between 1 and 3 is 1 minus 3, that's what V1 minus V3, and Y6 is the element which is connected between node 1 and 2. So voltage across 1 and 2 is V1 minus V2. So I have written that I1 is equal to Y1 V1, Y3 V1 minus V3, and plus Y6 V1 minus V2. So same thing if we applied at node 2, you can see here at the node 2, here I2 is connected to node 2, element Y2, admittance of the element Y5 and admittance Y6 of the element 6 connected to node 2. Same thing I have written here, I2 is equal to Y2 V2, that is element connected from 2 to ground is Y2. So voltage at that particular node is V2. Same time Y5 is the element connected between node 2 and 3, and the voltage difference between node 2 and 3 is V2 minus V3, plus Y6, and voltage is V2 minus V1. See here, in the previous case we are taken it as from 1 to 2. Here we are considering from 2, no? So it is 2 to 1. So Y6 multiplied by the voltage V2 minus V1 means it is the potential difference between 2 to 1. Same time at node 3, you can see here, node 3, no external current sources are there, but 3 elements are connecting, Y3, Y4, Y5. I am going to write it is 0 is equal to, so there is no external current, that is it is 0 is equal to Y3, that is the element connected between 3 to 1. So Y3 into V3 minus V1 plus Y4 V3, that is the element connected to node 3 to reference node, plus Y5 into V3 minus V2. So totally we are going to get three equations to three different currents or three different nodes by applying the KCL. So we can replace this with matrix form where I1, I2 and 0 at one side, and you can simplify it and take common. We can write it as Y1 plus Y3 plus Y6 minus Y3 at the first row. Second row minus Y6 Y2 plus Y5 plus Y6 minus Y5. At third row minus Y3 minus Y5 plus Y3 Y4 Y5, and multiplied with one and another matrix, that is V1 V2 V3. So this is what the three different buses we got here. This is nothing but YBus, that is current of the three different buses, is equal to YBus into EBus. EBus is the voltage bus. YBus is nothing but the admittance matrix. So see, the middle one matrix is nothing but admittance matrix, bus admittance matrix. Here, by seeing this matrix, you can tell that it is a symmetrical matrix. See, here element 1 2 is same as 2 1, 1 3 is same as element 3 1, 2 3 is same as 3 2. Symmetrical matrix. And one more thing, see here, y11, y22, y33 are nothing but it's the sum of the admittances connected to that particular node. Means you clearly see in this figure, y11 is nothing but the sum of the admittances connected to node 1. Which are the elements are connected? See, to node 1, y1 is connected, y3 is connected, y6 is connected. So y11 is nothing but sum of these three. See here, is it y1 plus y3 plus y6? Same thing you see in the second node. Which are the elements connected here? y6 is connected, y5 is connected, y2 is connected. So this is nothing but y22 is nothing but sum of these three, y2 plus y5 plus y6. See, second one. Is it same as third one? Three elements are connected to node 3. Sum of those three admittances are nothing but y33. At the same time, these are the diagonal elements. Coming to off diagonal elements, it's nothing but negative of the actual admittance. See, from node 1 to 2, element connected is y6. Is it? See, 1 to 2 element connected is y6. In this one, we are going to take the same value with negative sign. Same thing coming to y13, which is element connected between 1 and 3, y3. Is it taken as minus y3? Same as the remaining one. So, what are the diagonal elements? A diagonal elements, which is called as YIA, means as I told you, y11, y22, y33. These are the diagonal elements of the bus admittance matrix, is equal to the sum of the total admittance values of all the element incident, means connected to that particular node. What are the off diagonal elements? And off diagonal elements Yij. So here y12, y21, y23, y32, y13, y31, like that of the bus admittance matrix YBus is equal to the negative of the admittance values of the connecting element present between the buses I and J. Let us see the one problem, how to solve with this problem. See, this is 3 bus system. 1, 2 and 3, their admittances are given. See, it is clearly mentioned all values are in admittances. From the element connected between 1 to 2 is having the admittance value J8. Element connected between 1 to 3 is having admittance value J4. And the element connected between 2 to 3 is having admittance value J8. And all the 3 buses are connected with 3 different generators. Each are having different admittance values. See, J4, J8, J4, like that. Okay, fine. So this is what the network or oriented graph I got from that particular given single line diagram. Nodes are 1, 2, 3 and different values I have taken. This is nothing but the oriented graph from this network. Okay, fine. You know this, how to draw this diagram and all. No need to explain once again. Same values I have put. So here we can write y12 is j8. Is it element between 1 to 2 is 8. Y13 element between 1 to 3 is 4. J4. Actually, I have not shown here j. All the values are with j because it is admittances. Same thing, y23 is j8. You can see this figure, you will come to know which are the values. So we know what is y11, element which are connected to node 1. See here, node 1, which are the element connected? Y12 is connected, y13 is connected, y10 is connected. Is it? See, same, y22 is what? Y22, y21 is connected, y23 is connected, y20 is connected. At the same time, y33 is also same thing, y30 is connected, y31 is connected, y32 is connected. And remaining off diagonal values are nothing but it's negative of its admittance values. Y12 is, that is what capital Y12, that is the parameter or element of the bus admittance matrix is nothing but minus of its actual admittances. Okay, fine. So we got this YBus. You can do it by your own. Anyhow, all the formulas are given and values are you are knowing. Just to put that values, you will get this admittance. This is what the admittance bus admittance matrix we got from the given figure. Same type of another figure I have shown here, but here all the values are given with the impedance form. You can see here impedance form and different parameters are given here. So this is what the single line diagram, what we can graph we can get from the single line diagram. I have written all the values because we want admittance form. So here all the values are coming in negative because the impedance are given. Reciprocal of that impedance will give you the admittance here. The same admittance whatever you are going to get here. Okay. So using that the same method which we have followed in the previous one, we are going to get this value. So this problem is for you as a homework. You have to do it by your own and you have to submit me by tomorrow. Thank you.